Afternoon, thanks for the opportunity to give this talk, and the ideas that I'm going to present today are very similar to the previous talk, but on a much more limited computational budget, and to offset the limited computational budget, I'm going to rely heavily on Gaussian processes. So the question that we want to study is drug-induced arrhythmias, which differ, that is a specific problem that we want to tackle. And the problem with drug-induced arrhythmias is that you can observe them only at the organ or tissue level, but they can be originated at the ion channel or cellular level. So it's a multiscale problem because the heart is a multiscale system. So just very briefly of how an arrhythmia can be initiated. So we have this kind of representation of a cardiac cell, and if we have a drug, for example this drug torsades, it might block a specific channel, in this particular case the hair channel, and if we apply a high enough concentration, we will reduce the current that can flow through the channel. So if we do a simulation of this, for example in an M cell, for the arrhythmic model, we can see that at some point the KR current is so reduced that there might be some calcium currents that channel that reactivates and gives rise to these late activations that are called early after depolarizations. So now if we look at the organ levels, these changes are reflected from a clinical perspective in the electrocardiogram. So drug-induced arrhythmias are characterized first by a prolongation of the QT interval, which is the time that it takes for the heart to activate and then go back to its resting state. And the specific type of arrhythmia that drugs cause is or that we're interested in now is called torsade points. So currently the current regulation faces on how much a drug blocks the hair channel and how much it prolongs the QT interval. But we already know, and this has been already said in this conference, that the QT interval is not really a good predictor of drug-induced arrhythmias because it is very sensitive but not very specific. So we think that we can build models that maybe can provide better understanding of this problem. So my talk will have 3 short parts, don't worry. I'm going to talk first about a multiscale model that we have developed to study drug-induced arrhythmias. Then I'm going to talk a little bit about the QT interval, and finally how we can use these models to predict the risk of arrhythmias. So going to the multiscale model, so we have to first define, if we want to build a multiscale model, we have to specify all the different scales, and we use the cellular level the O'Hara-Rudy model for ventricular cells and the Stuart model for the Purkinje network. We use the monodomain model implemented in finite elements, specifically in Abacus. And if we put all together at the organ level, this is how it looks like. We have all three different cell types for the ventricles, the Purkinje network in white, and the model has around 7 million elements. Because all the internal variables that we need to update, we add up to 250 millions, and if we want to solve 5 bits, we need to update the model 1 million times. So going directly to the results, this is the baseline model, how it looks if we don't apply any drugs. We have a well-defined QRS complex, a positive T wave, which are healthy times, and the activation is regular. Now if we apply a high-risk drug, and this was also mentioned in the previous presentation, such as quinidine, we see that our model spontaneously develops an arrhythmia, and if we take a closer look, we see that the early after depolarizations at the M cells are actually triggering this. So the first, to summarize this first part, we have this high-resolution model of cardiac electrophysiology, and the model spontaneously develops an arrhythmia when we apply a high-risk drug. Now we would like to focus on the QT interval. So as I told you before, the QT interval is currently used to determine whether a drug will enter or not the market. So we have this high-resolution model. As I show you, we can compute an ACG. We can compute a QT interval from there. But the problem is that this model is expensive. It takes about 40 hours using 160 CPUs. So if we want to do sensitivity analysis or uncertainty quantification, we cannot really do that. But on the other hand, I could take a small piece of the model and represent it as just a 1D cable, a string of cells. I could also compute an ACG from there, and I could also compute a QT interval. It will not be very accurate, but I can still do it. And with this, it is feasible to do sensitivity analysis and uncertainty quantification. So the question that we're interested is, can we fuse these two sources of information in order to predict the high resolution output of the model, in this case the QT interval. And for that we use multi-fidelity Gaussian process regression that was introduced by Professor O'Hagan. And the idea here is that we have now a combined data set of input-output pairs, usually the low fidelity, which in our case is the 1D cable, will be much larger than the high fidelity data set. And we make an assumption about that relates the low fidelity function that we want to approximate with the high fidelity function. And this is an autoregressive model which basically says that the high fidelity data is, in our case, a scalar parameter. This could be more complicated, times the low fidelity data plus a function that will explain the difference between the high and low fidelity data. So hopefully this function is much easier to approximate than the entire high fidelity function. And we place Gaussian process priors for the low fidelity and the delta function, and then we can do a regression. So here's a simple example. Let's say that I want to approximate the blue curve, but I can only measure these 4 red points because my model is really expensive to evaluate. So if I do a regular Gaussian process regression, I will get the red fit. But now if I also include 11 low fidelity points that are shown here in pink and do multi-fidelity Gaussian process regression, you can see that now the red and blue curves pretty much overlap. So I have improved my predictive power quite a lot. So this is exactly what we did for the QT interval. We blocked 7 ionic currents, which are thought to be important for drug-induced arrhythmias, from 0 to 60%. We had 400 1D samples, and we use a Latin hypercube design for the 1D samples. And we also ran 45 3D models. And for this we started with 10, and then we selected the points of maximum variance from the output of our multi-fidelity Gaussian regression. So in that sense I will include the points that will reduce the variance the most in my Gaussian process, and that will bring the accuracy up. So in the end I will end up with an emulator here that if I give how much I'm blocking all these 7 channels, it will return the QT interval in less than 1 second. So instead of running a new simulation. And we perform 5-fold cross-validation, and we got an error of about 5%, which we think is acceptable. So now that I have constructed this emulator, we can very easily do a sensitivity analysis. And in this case we use the elementary effects method, which is also known as the Morris method. And it's basically explained very simply, it's like some finite differences that I take in the parameter space, and I take many of them in different points, and then I can compute the statistics on these finite difference estimates. And for example, I could compute the mean and the standard deviation. And if the parameter is very nonlinear, I will expect a very high standard deviation. But it was shown that, for example, you could have like at first positive slopes and then negative slopes, and that they could cancel out. So later it was in the index, a new index was introduced where we take the absolute value to avoid those cases. So here we can see the results for our sensitivity analysis. Not surprisingly, the KR current is the one that prolongs the QT interval the most, and we also saw that there are some currents that can shorten the QT interval, which we thought it was interesting, specifically the L-type calcium current. So now we can also do uncertainty quantification to determine what's the relationship between concentration and block. Usually the experiments are repeated several times, and here we actually took some work from the group of Gary Myrams, where they developed a Bayesian hierarchical approach to estimate the coefficients of these curves that you can see here, which are the IC50 and H values. So we took 500 samples from there, from a data set that had free repeats for free concentrations of these 7 channels that we are interested for 30 drugs. So now if we make a cut at a given concentration of those lines that I just showed you, we'll get a distribution of blocks, and then we can pass this distribution of blocks through our Gaussian process regression, our emulator, and then we will get a distribution of QT intervals. And here I'm showing the 95% confidence intervals for the blocks at the nominal concentration of the drug, and finally in this last column, how the QT interval was affected. And we can do this for all 30 drugs pretty quickly. And you can see what is interesting here, and it's also in agreement with our sensitivity analysis, that the bigger the uncertainty in the KR channel, the bigger the uncertainty will be in the QT interval. So if we had to invest more time doing experiments, probably it would be better to spend it getting a better estimate of the uncertainties in the KR channel. So we can also do this in a concentration dependent way. So here we have the normalized concentration of the drug, and here we have how the QT interval is changing. And you can see that first we can have a mean prediction, also 95% confidence intervals, and also the probability density for the QT interval here. So purple, black would mean that we have a high probability, and white will mean that we have a low probability. Again, we can do this for 30 drugs, and you can see actually that the uncertainties can be quite big. Like here we could have a change pretty much from 0 to 80% for a large concentration. And this is just considering the uncertainties coming from the experimental data. I haven't included any uncertainty coming from other model parameters, which there are quite a lot. So we also did some validation. There is some data from a randomized clinical trial testing these 4 drugs, which actually block different ion channels. And we have a pretty good agreement considering the uncertainties, but usually the points lie very close to our mean predictions. So to summarize this part, we have used multi-fidelity Gaussian process regression to build an emulator that made sensitivity analysis and uncertainty quantification feasible. And we have shown that the QT interval predictions are highly sensitive to the experimental uncertainty of the drug response data. And finally, we would like to use this model to make predictions about drug risk. So now, as I told you before, the QT interval is not very specific. It's sensitive but not specific, so we would like to go beyond that because we have this model that can spontaneously develop torsade points. So what we did is we took our sensitivity analysis and now we are interested in studying these two channels. We have opposite effect on the QT interval. So one tends to prolong the QT interval and the other one tends to shorten it. So we thought that there might be some interesting interactions between these two channels. And also we would like to predict what is the risk of drugs. So now we are in a classification problem because we want to predict whether our model has or not an arrhythmia. So it's a binary variable. So to tackle this problem, we use a particle learning Gaussian process classifier. And the idea here is that we will use an active learning criterion that will adaptively sample the points of maximum entropy. So here I have a toy example. So let's say I want to approximate this boundary here that splits the point that are labeled with plus and the points that are labeled with a minus sign. So because my model is very expensive to run, I want to do that with the fewest number of points. So this methodology will start with, let's say, 10 points, and then it will recompute the classifier and put the next point at the location of maximum information entropy, which also is the point of minimum information. And we did exactly this for our model with these two channels that I mentioned. So on the y-axis we have the Kr channel, and on the x-axis we have the L-type calcium current. And with only 40 samples, we are able to get a really good definition of the boundary, because you can see that most of our samples are near the boundary. So here red means we saw an arrhythmia in the model, and blue means we didn't see an arrhythmia. So we did an experimental validation of this diagram using isolated hearts, and we started from a control with no drug. Then we applied dofetility, which only blocks the Kr channel, so we move up, and we saw an arrhythmia in the rat hearts. Then we apply another drug that only blocks the calcium channel, and we were able to revert the arrhythmia. So this is not saying that to avoid arrhythmias you should take such a high concentration of these two drugs. It's just showing a validation for that this phenomenon could be observed. So also, as the previous talk showed, we can see that drugs are lines of increasing concentration in this diagram. So if we take terfenadine, it will move along this path because it blocks these two channels in different ways. And we thought that this concentration, the concentration at which we enter this red region, could be an indicator of the risk of an arrhythmia. If this concentration is very low, we will expect that the drug has a high risk. But if we have another drug, verapamil, which was also discussed before, this drug will never enter the red region, and we will assume that it's a safe drug. Doesn't mean that it's safe for all the arrhythmias. It just means that for this particular type of arrhythmias, it will be safe. We did that with 23 drugs for which we know the risk, So the drugs that we know the risk are labeled with in red, and the drugs that we know that don't induce arrhythmias are labeled with green. So now if we sort them by this critical concentration, you can see that we can pretty much split the drugs into the two groups in two. So drugs with a low critical concentration are of high risk, and drugs with a high critical concentration are green, so they will be safe. Not saying that this is the best classifier, but it was a nice indication that our model can capture the behavior of these drugs. So we did this also more formally using lib1 outgrowth validation, because we had like very few data points and a Gaussian process classifier, and we were able to correctly classify 22 out of the 23 drugs. So to summarize this part, we have used a Gaussian process classifier with an active learning strategy to identify the arrhythmia region that otherwise would have cost us a lot of computational time, and we were able to correctly classify 22 out of 23 drugs. So I show you two concepts. So the first one was a multi-fidelity regression, and the second one was a Gaussian process classifier with active learning. And it would be really nice to combine these two concepts, and we currently have a poster where we have extended the multi-fidelity Gaussian process regression to a classification case, and you can stop by after I finish in a couple of minutes, and I will be in with my poster if you're interested. So to summarize, we have used multiscale modeling that was aided with Gaussian processes to reduce the computational time, and that allowed us to do uncertainty quantification, sensitivity analysis, and also predict the risk of drugs very quickly. And we can of course use these techniques beyond electrophysiology and drug-induced arrhythmias. So some of the future work is to use multi-fidelity classification for drug-induced arrhythmias. Also do, because we already built this classifier, we can also very quickly do uncertainty quantification for the drug risk prediction. The problem there is that there's a mismatch between the data for which is very well characterized from drug response data and the drugs that we know very well if they induce or not arrhythmias. And also we can study other kinds of contractilities if we also build mechanical cupping, which is something that we are also working on. So this was I had a lot of collaborators during this work, and I would like to acknowledge them, and also my funding sources. And with that, I will take any questions.
Hi. Megan Lancaster from Eric Sobey's group had a study about 3 years ago that had the same essentially conceptual underpinnings, I think, of your third study, the machine learning classifier, where you used IKR and L-type calcium current.
Yep.
They used APD and intracellular calcium concentration.
Yep.
Essentially showed that if you just think about IKR, you simply can't classify. I'm wondering if you view your approach as complementary to theirs or overlapping, because it seems quite similar.
No, I mean, I feel like there is a lot of competition to build the best classifier for this application, but I feel that our contribution is more to show that this was an emergent phenomena in the 3D model, and we have a very good agreement with drugs that we know. I don't think this model will be incorporated by the FDA to predict the risk of drugs. So I see that is complementary, because this is very mechanistic. I mean, we just have a model, and it spontaneously developed arrhythmia. So we didn't pick certain features of the cellular activity to build our classifier. Yeah.
I've got one for you. So the misclassified drug is amiodarone. Have you got any sense as to why that was misclassified by your model?
No, it's actually not. Surprisingly, it's not amiodarone. It's this one. I'm terrible pronouncing drug names, but it's because basically when you're doing leave-one-out cross-validation, and to break this drug, you will suppress this drug and place the classification boundary somewhere here, and then it will be misclassified. So this is also like very sensitive to the data set that you're using and things like that. Yeah.
Any other questions?